Welcome you all to the new session of computer graphics. Today we will be learning about 2D scaling. Now in the previous session we have learned that there are various types of two-dimensional transformations or different changes can be performed on an object. And in the previous session we learned how translation works. Translation is nothing but the change in position of an object along a straight line path. So today we will see what a scaling is. Okay, so scaling is a change in size of an object. Change in size means either I can enlarge an object or we can shrink the object. Enlarging means object size is increased and shrinking means the size of the object is reduced. So either by increasing the size or decreasing the size you can make a change in object size. So if a triangle is given to you, you can either reduce the size of the triangle or you can enlarge the size of the triangle. Okay, in both these situations you are changing the size of the entire object. Now to apply scaling to an entire object, what we have to do? Just as we discussed in the case of a translation, to apply scaling for an entire object, you have to apply scaling transformations to each of its points. Only when you apply scaling transformations to all the points of the object, only then the object will be scaled to its new size. Clear? Now let us move on to the transformation equation. These are scaling transformation equations. Equation says x dash can be obtained by multiplying x and sx. That is, x dash is equal to x into sx. Similarly, y dash is equal to y into sy. X and y are xy coordinates of the current point. X dash and y dash are xy coordinates of the scaled point. That means if this is the current point, then xy corresponds to xy values of this position. And after scaling, let this be the new position. So I am going to scale this point to a new point. So x and y corresponds to xy coordinates of this position and x dash y dash corresponds to xy coordinates of scaled position. So similarly, we have to scale this point also and we have to scale this point also. Only then the entire object will be scaled. Okay. So the equation is x dash is equal to x into sx and y dash is equal to y into sy. So we know what is x and y and what is x dash y dash. What about this sx and sy? Sx and sy are together called scaling factors or scaling parameters. Okay. So as I said in translation, we have to add the translation factors to the xy values. But here in scaling, instead of adding, you have to multiply the scaling parameters to the xy values. Only then you can get the new xy positions. Okay. Now the same equation can be written in terms of point also. X dash y dash corresponds to the new position and can be written as p dash. Xy corresponds to the previous position, that is position before scaling, and it can be represented as p, and sx and sy together can be represented as scaling transformation, which is s. Now this above equation can also be represented in the form of a matrix. Let us see how it can be done. The point p dash, that is point obtained after scaling, can be represented as x dash y dash in the form of a matrix. Now the point P can be represented as x, y. The matrix, scaling matrix S can be represented as Sx 0 and 0 Sy. Now the reason for writing the matrix like this is, when you will multiply these two matrices together, you should get this equation. Let us see how. So first row should be multiplied by this column to get the value of x dash, and second row should be multiplied by this column to get the value of y dash. Let us write x dash is equal to sx into x, sx into x plus 0 into y, which is 0. So equation of x dash is equal to x sx. Got the equation, same as here. Now y dash equal to this row into this column. Y dash is equal to 0 into x. You will get 0 plus sy into y, that is y into sy. So the equation for y dash is equal to y into sy, and x dash is equal to x into sx. So by writing the matrix in this form, when you will multiply these two matrices, the result will be same as these equations. So in this way, scaling can also be represented in the form of a matrix or can be represented as a transformation equation. Okay. Now comes homogeneous coordinates. As I told you in the previous session, a homogeneous coordinates means you can represent an n coordinate system using n plus 1 coordinates. That means we are now talking about a 2 coordinate system. Here we are having only 2 coordinates x and y. So the 2 coordinate system can be represented using 2 plus 1 coordinates, which is 3. Let us check how these 2 coordinates can be represented using 3 coordinates. So x dash y dash will become x dash y dash 1. Here we are having only 2 coordinates and it is now represented using 3 coordinates. Now comes x, y. Again the 2 coordinates system is represented using 3 coordinates, x, y, 1. So that the third coordinate is a constant value, which is 1. Now comes this scaling matrix. Remember, this is a 2 by 2 matrix, and now I am going to write a 3 by 3 matrix. So that x dash can be obtained when first row is multiplied by this column. Y dash can be obtained when second row is multiplied by this column. And one third value 1 can be obtained when third row is multiplied by this column. Let us check. X dash is equal to x into sx, x into sx, plus 0 into y, plus 0 into y is 0. Again plus 0 into 1, which is also 0. So by this we will get the equation x dash is equal to what? X into sx. We got the first equation. Let us move on to the second equation, which is y dash is equal to second row and this column, 0 into sx, which is 0, sy into y, y into sy, and plus 0 into 1, which is also 0. So these two terms are 0. So equation for y dash is equal to y into sy. You got the second equation. Now comes the third value. 1 is equal to 0 into x. 0 into x is 0, plus 0 into y, which is also 0, plus 1 into 1, which is 1. So 1 equal to 1. You got all the 3 equations. Still the value is not changed. You have represented the 2 coordinate system using 3 coordinates and the value is still the same. When you will multiply these 2 matrices, you will get the same equations as above. So this is how you can represent scaling using homogeneous coordinate matrix system. Let us write the corresponding point representation. This corresponds to point P dash, this corresponds to point P, and this corresponds to the scaling matrix S. Now as I said in the previous session, P dash can be obtained when P is multiplied to S, or I can say like this. This is the initial point. When the initial point is applied a scaling transformation, you will get the new scaled position. I repeat, when you have an initial point and when the initial point is applied a scaling transformation, you will get a new position, which is a position obtained after scaling. So you have to take the equation from right to left. Okay, initial point, do the scaling, and you will get the final point. Clear? So this is all about scaling transformation. Now let us work out with a few examples. Consider a triangle with the points given as 4, 5, 1, 8 and 6, 8. Okay. The scaling parameters are also given. Value of Sx is 2 and value of Sy is also 2. What we have to do? We have the initial points and we are having the scaling parameters also. Now using the scaling equation, which is x dash is equal to x into Sx and y dash is equal to y into Sy. Using the scaling equation, we will find the new position of this triangle, which is obtained after scaling. How we will find the new point? Substituting the values of x, Sx, y and Sy, we can easily find the values of x dash and y dash. So the triangle is having 3 points. Let us first scale this point 4, 5, where the value of x is 4 and the value of y is 5. So to get the new position x dash, we have to multiply x with Sx and y with Sy. So 4 into 2 we will get 8 and 5 into 2 we will get 10. So before scaling the position was at 4, 5 and after scaling the new position will be at 8, 10. Similarly I am going to scale this point 1, 8. Now the value of x is 1 and y is 8. X into Sx, 1 into 2 you will get 2. Y is 8 and y should be multiplied by Sy. 8 into 2 you will get 16. 1 into 2 is 2 and 8 into 2 is 16. So the next point is 2, 16. Initially the point was at 1, 8. After scaling it will move on to 2, 16. Now I am going to scale this point 6, 8. Value of x is value of x is 6 and value of y is 8. X into Sx, 6 into 2, 12. Y into Sy, 8 into 2, 16 written. So initially the point was at 6, 8 and after scaling new point is at 12, 16. So the triangle can be drawn at positions 8, 10, 2, 16 and 12, 16. So in this way, using scaling equations, you can apply scaling transformations to all the points so that the entire object is scaled. Okay. Now let us take another example to learn a few more properties. Suppose this is a graph and we are having a small square. The points of the square are 1, 1. This point is called 1, 1. First we have to specify the column number, then we have to specify the row number. So this point is at 1, 1. This point is at 2, 1. This is at 2, 2. And this is at 1, 2. So the points of the entire unit square are written over here. Clear? Now we know the initial points. There are 4 points to a square and I am going to scale this square. Scaling values are given as Sx equal to 2 and Sy equal to 2. So using the initial points and the scaling parameters, I am going to compute the new points. How? Each x, these are all x values and these are all y values. For each point, every x will be multiplied by Sx and every y will be multiplied to Sy. So 1 into 2, 2. 1 into 2, 2. So 1, 1 scaled to 2, 2. Next comes 2, 1. 2 into 2, 4. 1 into 2, 2. 2, 1 scaled to 4, 2. Similarly, find the corresponding scaling positions for this point and this point also. When you take each point, substitute the value of x as the first parameter and substitute the value of y as the second parameter given in this point. Okay, so this all the first parameters corresponds to values of x and all the second parameter corresponds to values of y. So after obtaining the new xy positions, what you can do? You can plot them on a graph. So I'm going to plot the points 2, 2, 4, 2, 4, 4 and 2, 4. When all these points are plotted, what change do I observe? This was a small square. After scaling, the square size enlarged. That means size of the square increased. One more thing. When Sx and Sy both are having same value, when Sx is equal to Sy, it is called a uniform scaling. That means we are enlarging in both directions. That is in horizontal direction and in vertical direction. Equal increase in size is occurring in both these directions. One more thing. When Sx and Sy are greater than 1, here we can observe that both these values are greater than 1. Then when both the values are greater than 1, size will definitely increase. Let us take another example. So in the previous example, we have learned that when both the parameters are equal, it will be having a uniform scaling. That means in horizontal direction as well as in the vertical direction, we will be having equal increase in size. And when both these parameters are greater than 1, the size of the object will definitely increase. So let us take another example where I am plotting a small square and the points of the square are at 1, 1, 2, 1, 2, 2 and 1, 2. These are the initial points. Initial points are written and the scaling values are Sx equal to 2 and Sy equal to 1. Remember, values of Sx and Sy are not equal. Okay. Now what happens? Using these scaling parameters, I am going to compute the new values. So these are the initial values and these are the scaling values. Using these two things, I am going to compute the new values. So every x will be multiplied by Sx and every y will be multiplied by Sy. That is 1 into 2, you will get 2. 1 into 1, you will get 1. Second point, 2 into 2, you will get 4. 1 into 1, you will get 1. Third point, 2 into 2, 4. 2 into 1, 2. In this way, for every point, you have to compute the corresponding scaled value. So after obtaining all the scaled points, you have to plot the corresponding points on the screen. And when you closely observe the picture, you can identify that initially it was a small square. But after scaling, the size has increased only in the horizontal direction. Height has not increased. Height of the initial object and height of the scaled object both are same. This is because the scaling parameter Sy was 1. When you will multiply the value with 1, you will get the same value. So this means when Sy equals 1, it indicates that there is no change in vertical direction. There is only change in horizontal direction. That means size increases in horizontal direction. When the size of a square increases in horizontal direction, it will become a rectangle. So it was initially a square, now it became a rectangle. So size increased or the width increased. Taking another example, when this same square is taken with the same initial points, but I am just changing the scaling parameters Sx equal to 1 and Sy equal to 2. That means now again both of these are different values, but this time I want to change the y direction, but I am not changing the size of the object in the horizontal direction, therefore Sx equal to 1. So this time there will not be any change in the horizontal direction, only the size changes in vertical direction. Let us find the new points. So using new values of Sx and Sy from the initial points, multiplying every x with Sx and every y with Sy, obtain the corresponding scaled points and then plot them on the graph. Now you can observe that it was a square initially, and after scaling the object's height increased, but there is no change in the width. This is because Sx equal to 1, that is, there is no change in horizontal direction. Object size will not be changed in the horizontal direction, but since this is not 1, only the size of the object will be changed in the vertical direction. That means in this situation width will be same but height will increase. But here, since Sy equal to 1, height will be same, and since this is not equal to 1, width will be increased. So this is the difference. When a particular scaling parameter equals 1, this means there is no change. So if Sx equal to 1, no horizontal size increase. If Sy equal to 1, no vertical size increase. So in this situation, only size is increased in the horizontal direction, that means only the width increases, and here only the size is increased in the vertical direction, that means only the height increases. And in both these situations, both Sx and Sy are different. When Sx and Sy are both different, it is called a differential scaling. Clear? So in all the previous examples, we have learned how both Sx and Sy became equal. When these two are equal, it contributes to uniform scaling. When these two parameters are not equal, it contributes to a differential scaling. Then second property we learned was that when Sx and Sy, the values of these two scaling parameters are greater than 1, then the size of the object will increase. But what will happen if both these values are less than 1? Let us see this with the help of an example. Consider a graph where a square is plotted and the initial points of squares are at point 2, 1, 3, 1, 3, 2 and 2, 2. Now the scaling parameters are given as Sx equal to 0.5 and Sy equal to 0.5. Both these values are less than 1. Sx and Sy are less than 1. Using the initial points and the Sx, Sy values, I am going to compute the new values. That means x values will be multiplied by Sx to get the new x value, and y values will be multiplied by Sy to get the new y value. Taking each point, using the scaling transformation equation, compute the corresponding scaled point. So there are 4 initial points, so 4 scaled values will be there. After finding all these scaled values, let us plot it on a graph. So when the scaled points got plotted on the graph, what do we observe? Size of the object reduced. So this is all. When Sx and Sy values are less than 1, then the size of the object will reduce. So what are the things that we learned today? When these two are equal, it is a uniform scaling. When these two values are different, it is a differential scaling. When these two values are greater than 1, size of the object increases. When these two values are less than 1, size of the object reduces. When Sx equal to 1, only the height of the object increases, and when Sy equal to 1, only the width of the object increases. So these are the different things you have to consider while learning scaling. Now let us move on to a different topic, which is called fixed point scaling. Fixed point scaling means you are scaling the object by keeping one point as a fixed point. That means suppose I want to scale a triangle and I am going to do a fixed point scaling, which means you have to keep one point as fixed. That means you cannot scale one point. Keeping a point as fixed, you can apply scaling to all other positions. That means I can scale this position, I can scale this position also, but this is a fixed point. Clear? So suppose there is a small square and let this be the fixed point, which means except this point all other points will be scaled, and this point will not undergo any scaling. Okay, so scaling an object by keeping only one point as a fixed point is called a fixed point scaling. Now the equation for fixed point scaling is x dash is equal to xf plus x minus xf into sx, and y dash is equal to yf plus y minus yf into sy. We know what is sx and sy. These are scaling parameters. What is this x and y? If I am going to scale this point, then the xy values of this point will be substituted here in y. After scaling, the new position to which the object is scaled, that new position's xy values will be found in x dash and y dash. What is this xf and yf? This is the fixed points x value and fixed points y value. So x value at this position is xf, y value at this position is yf. So this is the original point to be scaled. This is the xy values of fixed point. These are the scaling parameters, and these are the points obtained after scaling. In this way, using these two equations, you can find the new scaling points in fixed point scaling. So this is all about everything about the scaling transformation. Hope you understood. Thank you.